Hi, we're on Chapter 13, Kinetic Molecular Theory. And we're going to talk about each of the states of matter. Now, you already know my famous dance of solid, liquid, gas, plasma. So that is what the kinetic molecular theory is. You know that in a solid, everything is moving, but it's vibrating. That's why I kind of shiver. Then in a liquid, it's kind of moving, but it's still touching each other, so it's moving a little bit faster. There's a little bit more energy. And then finally in gas, it's really energetic, and plasma is super energetic, and so it gets boom, okay? We're going to go into more detail about the particulars of the kinetic molecular theory now in this section. So we know, if we look at a weather map, that we have highs and lows. If we know about hurricanes, it all has to do with temperature and gases in the atmosphere. So this is what makes our weather, is temperature, wind, which is the flowing of the gases, and how it affects our atmosphere. We'll talk about that later in this presentation. Okay, we're going to specifically talk about gases in this case. Okay, so let's look at three assumptions that apply to gases. Okay, the first thing we have to think about is, what does kinetic mean? Kinetic has to do with motion. And energy that has to do with motion is called kinetic energy. So kinetic theory has to do with the fact that particles are in constant motion. That's what I was saying, even solids are in constant motion. Gas are really moving around fairly rapidly compared to the other states of matter, except for plasma. So the particles in a gas are molecules or atoms. For instance, the noble gases would be atoms, and something like carbon dioxide would be a molecule. Okay, these are some fundamental assumptions about these gases. The particles in a gas are considered small. Okay, so let's very carefully look at this idea. Okay, they're small. They're hard spheres, meaning kind of like if you think about Dalton's idea of an atom, and insignificant volume. So we don't really have to worry about the volume of the individual molecules of gases. Okay? So we're looking at, if we look at volume, we're looking at a larger amount of gas. Within the gas, the particles are really far apart. So if I was to draw a box full of gas and draw dots for each molecule, they would be all over the place, okay? And they're pretty far apart compared to a liquid where they're touching each other and are organized in a solid. And between the particles, there's lots of empty space, okay? So there's all this empty space in there. And now, this is very important. The third thing is there's no attractive or repulsive forces exist between the particles. We know from previous discussion that there are van der Waals forces, but they're so tiny that we are going to consider them insignificant. So for the KMT, for a gas, you have small hard spheres with insignificant volume. They're far apart. There's lots of empty space, and there's no attractive forces. So they're moving randomly. Okay. Then there's some other assumptions. Okay. The gas, the movement of the gas is rapid, constant, and random. Okay, so if we have all these in our container and it starts down here, they're going to move till they fill the whole container up. So there's going to be lots of empty space in between them, but the gas is going to fill the whole container up. So it takes the volume of the container. And if we opened it, it would spread out continually. All right, the rapid constant motion of the particles in the gas causes them to collide. So they can collide with the walls of the container. And what this does, it forms pressure with the frequency of collisions, and they can also collide with each other. Okay? So this constant collision is going to increase the pressure. Okay? And the other part is we're going to assume that these gases travel in straight lines because that's the quickest distance between, the shortest distance between 2 points. So they're constantly moving around in straight lines until they collide with another particle. And then it's kind of like a billiard ball, and it will hit each other and move apart and move backwards. And they change direction only when they rebound from these collisions. So a particle of gas will continue on its merry way until it reaches an obstacle. Okay, we're going to call these collisions elastic. Okay, and what does elastic mean? So in elastic collisions, okay, kinetic energy is transferred without loss from one particle to another. So if you have two particles with a certain amount of energy, and when they hit, there's no loss like as heat. It's completely transferred to one or the other. So say this one was stationary and this one hit it, and this would become stationary and this would move away at the same speed as the other if it's the same mass. So the total kinetic energy remains constant. Otherwise, they might hit each other and one gets faster, one gets slower. Okay, so I'm going to ask you what an elastic collision is between gas molecules on on plate posit, and let me give a little break. Okay, I hope you got the fact that an elastic collision is where the kinetic energy is transferred from one particle to another with no overall loss of kinetic energy. Okay? That's the important characteristics. Okay, I mentioned gas pressure previously, but we can use kinetic theory to explain this gas pressure. Remember I said the gas pressure results from the force that's put on the surface area of the object. Okay? So if you're in a closed container, the gas keeps on hitting it, and this is the collisions we're talking about, and so it exerts a force. That's going to be pressure. So gas pressure comes up from this force when they collide with either each other or the container's walls. So there's billions of these moving particles in a small space, and they're simultaneously colliding in the object, so that can build up pressure. So for instance, here's my box, and if I have 4 in this box, and I have 1, 2, 3, 4, 5, 6, 7, 8, I should draw the same size boxes. So imagine these two boxes are the same size. This is going to be much more pressure because there's going to be more collisions because there's more gas particles than this one. Okay, so if it's empty, there's no pressure, so you're in a vacuum. So a vacuum does not have, a true vacuum does not have any particles in it. So a vacuum is when you have no particles in pure empty space. So empty space is a vacuum. Technically, outer space is a vacuum, but there are particles, but they're so far apart that for all intents and purposes, you're in a vacuum situation. Now, one of the things you should think about is that air is a fluid, not a liquid, but a fluid. Just like a liquid is a fluid, gas is a fluid. And since air is made up of gas particles, they have mass. And basically, our atmosphere has mass. Now, if you think of going down in the ocean with all that water on top of you, it gets more and more pressure the further you go down. Well, here at sea level, there's an ocean of air above us. So we have a high amount of air pressure, and we call that 1 atmosphere, or 760 millimeters of mercury is the pressure at sea level. Now, if we go up into the higher levels of the atmosphere, there's less particles. So if you go to a mountain top, it's harder to breathe because there's less oxygen, and the air pressure is less also. So what causes this air pressure? Again, it all goes back to collisions. You're going to see this word over and over again. Collisions, okay, of gas particles and molecules with objects is atmospheric pressure. It decreases as you climb a mountain, and it increases, of course, as you decrease. Okay, if you think of it this way, here's my mountain, here's my sea level. So here's the top of the atmosphere. There's a lot more volume between the sea level and the mountain. So there's less dense, it's less dense here. There's a lot greater density here. All right? Okay, a man named Torricelli created something called the barometer. Okay, and right here we have a tube filled with mercury. Now, the way I would do this is I would turn it upside down, fill it with mercury, put my finger over, which is not the best thing to do with mercury, but I would put my finger over it, put it underneath, and then right here is a bowl full of mercury. Let me go back. And I would put it there. So what's happening, these arrows represent air pressing down on this mercury. And so actually what happens is it pushes the mercury up to the top of this tube, okay, depending on the air pressure. Now this area here is a vacuum, okay, because when I filled it up, what happened was it kind of, a little bit of it came out to adjust for air pressure. So as the air pressure decreases, more of the mercury comes out because there's less pressure, less force pushing down on it. So here on top of Mount Everest, we see a much lower amount of mercury than we see at sea level. Okay, so it's because of the sea of air, there's more of it at sea level compared to a less dense amount here, so the mercury is free to come out. So it balances this column of mercury. Okay, so what's going to happen to this column of mercury when a low pressure system is moving into your region? In other words, you have two directions. It can either go up or it can go down. Okay, it really depends on something, on that. Okay, it depends if it goes up or it goes down, depending on it. So if you're going to lower pressure, what's going to happen to the column? Think about what we just saw on the previous page. And try to explain that. This will be on Play Pause It. Okay. So as the storm approaches, the column, of course, goes down because it said low pressure, so therefore it's going to go down. Okay, the unit we use in SI is pascals, and usually we use kilopascals because a pascal is a very, very small amount. A kilopascal is more at the average of normal atmospheric pressure. We can use 100 of those rather than 100,000 pascals. So it makes the math a little easier to use kilopascals. Two other units that are used, the original unit was millimeters of mercury, and really in chemistry we use atmospheres a lot. 1 atmosphere is equal to 100 kilopascals, or 760 millimeters of mercury. I'm going to write that for you. It's something that you should know. I expect you to know that. So there's 760, and there's 1 atmosphere, which is equal to 100 kilopascals. Excuse me. So those are your 3 things. Okay, and there they are right there. And actually, if you round it off correctly, it would be 101.3. All right, a standard atmospheric pressure, we also say it's at 25 degrees Celsius, okay? So these are equivalent values. If we wanted to do conversions using factor label, we use this identity. So it's very important for you to memorize these 3 standard pressures, okay? So you will also see something called STP, standard temperature and pressure, okay? So standard temperature and pressure, okay, is a little bit different than just standard atmospheres. STP is at 0 degrees C, okay, rather than 25 degrees C. And so we have 101.3 or 1 atmosphere. Okay, this is not right. All right, let's do some conversions. I'm going to ask you to do the math for it. Okay, so I'm going to ask you 2 questions. One is to convert 450 kilopascals. Well, actually, I'm not going to put it on play pause yet. I'm going to show you how to do this. All right, so here we have 450 kilopascals. We know that 1 atmosphere is 101.3 kilopascal, and 1 atmosphere is 760 millimeters of mercury. We want to know the pressure in atmospheres in millimeters of mercury. Okay, so our conversion factor is 1 atmosphere to 101.3 kilopascals, or 760 millimeters of mercury to 101.3 kilopascals. So if we do factor label, we have 450, 1 over 101.3, so it's 4.4 atmospheres, or we have 450 kilopascals and 760 millimeters of mercury over 101.3 kilopascals equals 3,400, 3.4 times 10 to the 3 millimeters of mercury. So make sure you think it makes sense. The first conversion factor is much less than 1, and the second is much greater than 1. So the first one gives you a smaller value, 1 here, 1 atmosphere, oops, 1 atmosphere over 101.3. So 1 atmosphere over 101.3 should give you a smaller number. 760 over 101 should give you a bigger number. It makes sense. Okay, what should be the pressure inside a vacuum? This is going to be on plate pause. Excellent. 0. There's no pressure inside a vacuum. Okay, kinetic energy and temperature. Now this is a very important concept too. Kinetic energy and temperature are related, because what is temperature? Temperature is defined as the average kinetic energy of particles. So it's the movement, the average movement, not of single ones, but of a large amount of particles, because they're all moving probably at a slightly different speed. So whatever the average amount, so the faster they are moving as a group, if the average is much higher, it's a hot temperature or higher temperature, and if they're moving very slowly as a group, it's a lower temperature. So as you think about it, when you heat a substance, the particles absorb energy and they move faster. Okay, so that stored energy, okay, does not raise temperature, but the remaining absorbed energy does speed up the particles. That is, increases their kinetic energy. So some of it is stored, but most of it is actually transferred into movement, which that movement then results in an increase in temperature. Okay. As I said, it was an average. Okay, so it's somewhere in the middle of the range of all the particles moving. And so we can say, no matter what form of matter we have, solid, liquid, or gas, if the temperature is the same, the average kinetic energy of those particles, so a solid at room temperature, that vibration that's happening inside the solid is as fast, mass is as fast basically, or the average kinetic energy is, let me put a formula there for you, is 1/2 mv squared. So it's the mass of the particles times their velocity squared, or their speed squared, and that's their average kinetic energy. Okay? So if that's their average kinetic energy, then what we're doing is we're saying that maybe the mass of a solid is larger than this, but they have the same kinetic energy. So they might not be moving as fast, but the mass might be bigger. Or if they're at the same amount, but different substances, this relationship would give you the same answer at the same temperature. Okay, so if we look at these two graphs, what they show us is at a lower water temperature, your average is closer to 0 than at a higher temperature. So if you have the same amount of water particles, you're going to get this very high peak because it's under a smaller area, and then as you warm up, it goes to, there's some that are still lower, some much higher. So cold versus hot water. Okay, so the temperature is related to how fast the average amount of kinetic energy is present. When the substance cools, the particles start moving slower, the average kinetic energy decreases, and therefore it slows down and the temperature goes down. Now, we use Kelvin more than Celsius when we talk about gases especially. Absolute zero is theoretically the place where all motion ceases. All right? And we can't get any lower than that, so that's why we call it absolute zero, because movement ceases. And this is minus 273.515 degrees C. This is very important also for mathematical purposes to not have negative numbers. Okay? Now, we've never gotten to absolute zero. Okay? We have gotten to 0.1 or 1 times 10 to the minus 9 kelvins is the closest we got, which is pretty close. Okay, the coldest temperature are way out in space, far from a sun. Now, if we use Kelvin temperatures, Kelvin temperature of a substance is directly proportional to the average kinetic energy of the particles. Okay, checkpoint. You'll see this on play posit. What is the result of increasing the temperature of a gas sample? If you picked C, you did well. Okay, here's some summary. You know what to do. Turn it off, take some notes. Some definitions. Okay, that's the end of the first video.